In this video, I will go over linked lists, like what are linked lists and when to use them, as well as how to use them, and some practice using linked list operations. To start, here's what a linked list looks like and what are the main components of a linked list. Each one of those are called nodes. So a linked list is a collection of nodes, and these nodes contain two main things. They contain data and the next. The data could be any data type like an integer, string, and the next is basically a reference pointer to the next node. We keep track of the first node in a linked list as the head, and in some implementations we also keep track of the last node as the tail. And again, so it's a collection of nodes with data and a next pointer, and the last node points to null. So what are linked lists? They are data structures. And they're very similar to arrays in which they store elements of the same type. Linked lists are different from arrays as they are not continuous. So if you remember, in arrays, elements were stored one after the other in memory. So we were able to access the elements very quickly if we're able to know their position or index. However, in linked lists, let's say we have linked lists of 1, 3, 5, and 7. So these nodes are connected through these pointers, but they're not continuous in memory. So we keep track of them through these pointers, but they're not stored in a continuous order. So we're not able to randomly access the elements by their position. And again, so this is the head. This is called the next, which is a reference. Each one of those are called nodes. And this one at the end here points to null. We have two main types of linked lists. We have singly and doubly. Singly is what we looked at in this example. It's basically a collection of nodes with a next pointer. As for doubly, it's similar to singly, however, it also has a previous pointer or reference, which points to the node before it. And circular could be both singly and doubly, or doubly. Plus, it has a feature that the last node points back to the head. So let's look at some images here. Here's an example of a singly linked list. It's basically a collection of nodes with a next pointer. And here's a different implementation where we keep track of the tail at the end. As you can see, a doubly linked list is similar in which it has a next pointer for every node, plus there is a previous pointer. So the head node here, A, has a next pointer to B and a previous pointer to null, since it is the first element, so there's nothing before it. The last node also points to null as there's nothing after it, and its previous is the one before that. And this is an implementation where we keep track of the head. Here we have a circular linked list, which again could be either singly or doubly. The only difference is that it has an additional feature where we point back to the head at the last node, and in a doubly implementation, the head points to the tail and the tail points back to the head. So it's like a circle in which we have access to the edges as well. Okay, so we looked at what are linked lists and their different types and how they're different from arrays. So now, when do we use linked lists? We have four main operations in linked lists, and their time complexity at the worst case, big O, is big O of n for all of them. Let's say we have a linked list of 3 nodes. So we have 1, 2, and 4. And we want to insert, let's say we have this function called insert, and it takes 2 arguments. The value of the node we want to insert, so 3, and the position at which we want to insert. Say we want to insert position 2. Let's say those are also like positioned from 0 and so on. Since if you want to traverse like through a linked list, that will be usually through loops like a for loop or while loop, and the iteration starts from 0. So let's say we have 0, 1, 2 positions, and we want to insert at the second position, so at this one. So the way we do it is that, say we have this new node here with a value of 3. First, we have to find where the second position is, and that would require us to traverse through this linked list. So first go through the first node, then the second node, then iterate up to the one before it, and then we set this new node to point to the next of this node. So the next of the current node will be the next of our new node. And then since we have a connection here, now we can change this pointer to point to our new node. And now we have added the new element at the second position. So as you can see, it takes big O of n, since we have to first traverse to the position we want to insert at, then we perform the insertion. And in the worst case, it would be big O of 1 if it was like inserting at the head or tail, since we don't have to do any traversing or anything. It's always take us constant time. And the same thing is for deleting elements. Accessing will also take big O of n in the worst case, because we would also have to go through the whole linked list in the worst case, which could be of size n, and access that element at the last index. In the best case, it would be the first or last index, so the head would just take constant time, or the tail if we keep track of it in our implementation. And same thing for find and so on. So what are linked lists helpful for? Since the time complexity is not the best compared to some operations of arrays, the thing is that arrays are they grow dynamically. So grow dynamically. So if you remember arrays, they're static. Once you declare and initialize an array, its capacity is set and you cannot change it. We do have this thing called like array lists or vectors, which are arrays, but they have like a set of operations that require enable us to like double the capacity if we want to add like at a position that for an array that's already full in capacity. But this like requires adding a new array which takes much more space than linked lists. So Linked lists are helpful when you're not sure of the size of the collection of data, as it grows dynamically and does not take as much space as array lists. It's also useful when like inserting / deleting at beginning or end, since it's still constant time. So here's just another example of inserting an element. This is a doubly linked list. So first, this is the new node we want to insert, and it will be at position 1, since it starts from 0. So this new node, its next would be the element that's next to the one we're currently at. So let's say we have a current node that starts from here. The next of this would be equal to the next of this new node, and the previous of this would be our current node. And now that we have a connection here, we can change those two references to point to the new node. And this, it's important to know how like pointers work and stuff for these when working with linked lists, since, for example, if you point directly to the new node without having the connection here, you would lose track of the rest of the nodes. So this is another example of how it works. And now here's how the implementation works in C++. So linked lists have two main components. They have nodes and the linked list class. The node has data and next. As we saw earlier in the figure, each node will consist of these two elements. And in this case, I implemented it as a generic type. So it could be different data type based on how what the data is, so, and the values in it. And then the linked list has a head, which is initially just a null pointer. And we have a few operations here. These are the main operations. We have find, insert, delete, and remove, and access. So inserts, first find. It's basically just traversing through the linked lists. We use a while loop here since initially we don't have like a size or length of a linked list, so we just keep iterating through it until we reach the null pointer, which is the last element. So let's say we have a linked list of 3 elements, 1, 2, and 3, and then the last one points to null. So we keep traversing until we reach this null pointer. That's when we know we're at the end of the linked list. Then inserting, the way it works is like how I explained it earlier. We populate this new node, since insert takes a value, not a node, and a position. So we create a new node with this value, and then here we check for some edge cases, like if it's empty, if we're inserting at the beginning, and so on. But the main operation here is just finding the position. We set a current node to start at the head, and then we keep iterating and moving until we reach the position that we want to be at. And in this implementation, the way I did it is to stop at the position before the one we want to insert at, like how it was explained. Like if we want to insert at position 2, so this is 0, 1, 2, we stop at the one before it, so position -1, and then that's when we change the, let's say this is also 3, that's when we're able to like make this connection here through the currents next, and then setting the currents next to the new node, and so on. And for removing, it is essentially the same. Here we're checking for some edge cases, but we find the position, we create this current node which iterates through the linked list, and we also store the node that we want to delete in a temp node. So let's see an example again. So let's say we have 0, 1, 2, and 3, and we want to delete. So it takes in just one argument, which is the position. So 0, 1, 2. Let's say we want to delete this last element here, which is at position 2. So we go to the node before the last one, so the one at the position 1, and we store the next of it, which is the one we want to delete, in a temp node. Then we change the pointer to point to the next of the next of the ones we want to delete, which is just null in this case. And the reason why we store it in a temp is because after we change the pointer here, we lose track of this. And in C++ and C, we need to manually delete this node since there's no automatic memory management. And finally here, access takes a position and gets an element at that position. And here are a few more functions and operations that are useful, like display, reverse, sort. Those could be implemented in different ways, but they should have the same behavior. And in some implementations of linked lists, I found functions like set next or set previous. So you can create functions that would allow those pointer manipulation through those functions instead of doing it manually every time. And finally, we have a linked list class, and this is how we create it. We pass in the type here, so it's a linked list with a type int and a name list, and then we pass in. So we call the list dot the operation to be able to use that from the operations we have above.